All right. So before we actually get into these practice problems, I want to review the four main aspects of NMR. So we had number of signals. We had multiplicity / splitting. We had chemical shift. And we had integration. So integration was the number of hydrogens or carbons per signal. Chemical shift is basically telling us how shielded or deshielded something is. Multiplicity and splitting, remember, this is only for HNMR. A lot of people have forgotten that, so it's only for hydrogen NMR. And yeah, number of signals is pretty self-explanatory. So what I want you guys to review mostly is the basics of this, and then I want you to remember those like little nuanced things. So review enantiotopic versus distereotopic, and then complex splitting. And both of those things are in the notes that I sent out to you guys, or at least they should be. And we're going to go over it more when we do these practice problems. But in the meantime, let me stop sharing for one moment because I finally received the thing. I'm sorry, guys. Today has been quite a day. I feel like I sound not here. All right, share. Is she talking? Yes, I'm talking. Can you not hear me anymore? I hope you guys can hear me. Okay, so I got these random problems from a random set of problems, definitely not from anything that you have to do, wink, wink, nudge, nudge. So let's go through them together. So the first question is saying calculate the frequency of a chemical shift, blah, 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 blah. So calculation, the only calculation we had this semester was the chemical shift equation. Does anyone remember what the chemical shift equation is? Yes, Hertz over megahertz, ppm, Hertz, megahertz. So in this case, they give you the ppm, so it's 1.25. They give you 400 megahertz, and you need to find x. So at this point, you're doing 400 times 1.5, which would be well, you guys tell me that. Someone asked, the times 10 to the 6th isn't needed. Yeah, exactly. So in this class, you're not going to need to do times 10 to the 6th. But yeah, so x equals 500 because it's 400 times 1.25. And then for the second one, I'm going to draw out this molecule. So we have two of this group. So I'm going to draw O, O, and this is attached to a CH3. So it's asking what the splitting pattern of the HNMR spectrum would be for the bolded hydrogen. And so the bolded hydrogen is this one. So I will go ahead and draw those guys out. So the first thing we do in NMR is we look at symmetry. So this molecule has internal symmetry right here. So these signals and these signals are exactly the same. So these guys have 1, 2, 3 neighbors, and then does it have any neighbors on the other side? Okay, so why not? Because this technically is 1, 2, 3.
Don't you have to count the hydrogen bonding to the carbon? So it would be like 4 away, so not 3 away.
Yes, perfect. Okay, so something that people often get confused is that this one actually would be 4 bonds because this is 1 bond, this is 2 bonds. Cool. And then there's another reason as well. Oxygen in the way. Cool. So not only is it actually 4 bonds, not 3, but we're not going to split through the heteroatom. So if these guys have 3 neighbors plus 1, that equals 4. And we have a quartet. Any questions about the first two? We are looking at the blue hydrogens, so they're the bolded ones here and the blue ones here. Okay, cool. So which one of the following compounds would it be expected to show spin-spin splitting? So what the heck is spin-spin splitting? And you can either unmute and tell me, or you can say it in the chat. That's also fine. Just regular splitting, kind of, but there's like a asterisk to it. It's not complex splitting.
Does it involve like
That's okay.
different hydrogen environments?
Kind of. So yeah, so it's basically any multiplicity above 1. AKA you need to have at least 1 neighbor that is in a different environment. Cool. So if we draw out this guy, are any of these hydrogens higher than a singlet? No, cool, because there is a line of symmetry here, so there is only 1 signal and there is no splitting. Ta-da. So for number 2, we have 1, 2, 3, OCH3. So is there any hydrogen here that has a multiplicity above 1? This one also has no splitting, and the reason is the only hydrogens are those guys, and they're super far away from one another. So no splitting. Both of these guys are singlets. And then number 5 looks like this, and it's different because now we have an extra hydrogen signal. So does this guy have a hydrogen or have splitting? Yes, and the reason is because these guys are now neighbors. So this hydrogen has 6 neighbors plus 1. This hydrogen has 1 neighbor plus 1. So we're going to go ahead and say that this one does have splitting. Any questions? I'm so confused about what's going on in this building today. Okay. All right. So this is moving on to mass spec, and mass spec is cool because it's not too many rules, in my opinion. So when we're looking at an M plus peak that is 142, what do we automatically think about? Okay, so someone said it might be a nitrogen. So, but there's no nitrogen in the answers. Okay, cool. So usually when there's a question like this, at least one of them will be nitrogen in the answer choices. This one doesn't have any. But in this case, since it's an even number, it doesn't have nitrogens. Nitrogens are when we have an odd number. So even number equals no nitrogens. So every time they give you an M plus, I want you to make sure if it's even, there's no nitrogens. If it's odd, there's an odd number of nitrogens. So something that, okay, an even number of nitrogens would work, but he's not going to ask you, like, he's asking you something else if he gives you an even mass. If he gives you an odd mass, he specifically wants you to figure out how many nitrogens there are. If he gives you an even mass, he has to give you more information because it could be anything, if that makes sense. Okay, so at this point, we know it's not a nitrogen. Cool. So we know that the mass, the total mass, is 142. So we basically have to go through this and figure out which one of these guys have a mass of 142. And my little hack is in the side, I write carbon equals 12, hydrogen equals 1, oxygen equals 16. So for this one, I look at it and I'm like, okay, 11 carbons times 12, that's going to be around 130. And then, okay, so for this one, I can kind of guesstimate in my head and like look at it and be like, oh, that's kind of unreasonable. But I want you guys to do it on the calculator because usually you're going to get down to 50-50 and they're going to be pretty close to one another. So here we see 132 plus 10 because we have 10 hydrogens. That equals 142. So that works. This one, we would have 8 times 12, which is 96, plus 14, plus 32. So this one is also 142. This guy, 108 plus 18 plus 16. I don't know if you guys can hear it, but someone is playing music really obnoxiously loud in the background. And it's so freaking annoying. Okay. You can't hear it? Okay, cool. it just keeps blowing my concentration. So here we have 120 plus 8 plus 16. So this one equals 144. So your answer would be B. So someone asked, if you were to give us n+2 mass, which mass number would we use for bromine or chlorine? So for chlorine, you're going to use whatever is on the periodic table. For bromine, for the M plus peak, you use 79. For M+2, use 81. It depends, exactly. So for the M plus peak, you're going to use 79. For the M+2, you're going to use 81. So you would only use 80 for like the M+1, but he's not usually going to give you the M+1 because that's a weird thing to ask you about. This is driving me crazy. Give me one moment. Okay, I can still hear it, but it's not as bad as it was before. Alrighty. So the next question, which element contributes specifically to M+1? So what do we think? Ooh, someone was really quick to say carbon. Yes. Okay, so which one of these guys is not in M+1 at all? The O, exactly. So this is all M+1. This is M+2. And then the most significant contributor is going to be carbon because there is such a teeny, tiny percent of hydrogen and nitrogen isotopes, but there's pretty much the whole peak you see for M+1 is going to be the carbon isotope, which is carbon 13. Okay.
Rosemary?
Yes, what's up?
For the carbon, is it because carbon's bigger than nitrogen, hydrogen?
No, it has nothing to do with the size. It has to do with the percentage of isotope. So these peaks
Oh,
correspond to percentage of isotope.
and is it because
So
carbon has a lot of isotopes?
yeah, so the
Okay,
percentage of carbon isotope in the environment is like 1%, but compared to that, the nitrogen and hydrogen are like way insignificant. So even though that's already a small number, um, the other two are way smaller.
okay.
But very good question. All right. So any questions besides that, like about anything we've done so far? I always feel bad doing online sessions because I feel like it's very disconnected. I can't see you guys. We don't get that engagement in person. Um, but I hope it's still helpful for you guys. I hope you guys are still getting something out of it. Um, okay, so in the mass spectrum of an alkyl bromide and chloride, we have an intense what peak? Yeah, the format got messed up, but that is okay. M+2, cool. So the base peak, the parent peak are not going to change. The M plus peak is nitrogen, hydrogen, carbon. The M plus 2 peak is oxygen, sulfur, chlorine, bromine. So yes, M plus 2. I also don't know if you guys can hear me chewing on ice, but whatever. Okay, this question absolutely irks me because what the heck is that? Like, the numbers are disgusting, especially when this was in person. Absolutely awful. Yeah, but it's asking for the base peak, and so can someone tell me what the base peak is? How do we define the base peak? Yes, so the base peak is the highest peak, and it should be approximately 100% abundance, or intensity in this case. So we're looking for the absolute tallest peak, which would be 1, 2, 3, 4. Which one? Number 2, cool. And so even though you can hardly tell, this says 30. So we're looking for one that's ever so slightly less than 30. My safest bet would be B. Cool. So, So this question is asking for carbon NMR. So for carbon, well, for all NMR, we're going to look at symmetry, and we have internal symmetry here. So this is 1, 2, 3, 4, 5, 6. So we have 6 carbon signals.
Why would it only be 6 if like there's a dash and a wedge still? Like I see the internal symmetry, but at the same time, like isn't the double bond kind of breaking that symmetry?
So the double bond, I see what you mean. So what you kind of have to think about is the fact that the wedge and dash here just mean that these two are spinning around. And so this carbon is going to be here 50% of the time and here 50% of the time. And that's why it still has internal symmetry. So even though these two top parts are different, since this guy is going to spin around, this carbon is going to see both of these faces. This carbon is going to be both of these faces.
Okay, so if, for example, both of them were wedged or both of them were dashed, would there be 7 in that case, or still only 6?
So if you had, let's say, if you had something where there was like a double bond here or something like that, so this was stuck on a plane and these two sides were stuck, then yes, it would be different. But I feel like that would be visually too complicated for him to give you.
Okay, so just to clarify, so because those are single bonds and they can rotate around, um, I guess the asymmetry doesn't really matter, right?
Yes, and hold on, I'm trying to think of an example. I had one, but then it didn't work out. All right, so let's say something like that. Here we have OH, H. So we have something like this, right? At this point, this guy and this guy would be on the same side, this guy and this guy would be on the same side. So now these two would be different. And the difference here is that like this one has free rotation, whereas this one is stuck on the plane. Okay. Again, we're asking about carbon NMR, and this box is just a triple bond. So it's saying C triple bond N. So it's saying that which carbon is going to occur furthest downfield. And we know that downfield equals de-shielded. So are we looking for a higher number or a lower number? And I'm pretty sure this is also supposed to be a double bond. High, yes. Oh, it's a triple bond? There you go. All right. So we didn't really talk about the triple bond region, but the triple bond region is going to be somewhere between the heteroatom and double bond region. So which one of these guys looks the worst? It is B, and the reason it's B is because this guy is in the carboxylic region, which is, I believe, 190 to 220. Triple bonds are actually going to be less de-shielded. So they're going to be closer to 1. So they're going to be, I think it's between 6 to 8. But I would have to look that up. All right. Lightning round. What do we think of this? Enantiotopic. Cool, because we don't have any chiral centers present. Awesome. Okay. Vicinal coupling. What's vicinal coupling? And I know I skipped a couple, but I want to get through a bunch and then we can go back to the ones we skipped.
A, attached to adjacent carbons.
Cool. So vicinal means next door. So A is correct. Nope. Okay, which one of these is conjugated? Correct. It's going to be number 2 because conjugated is double, single, double. The only one that follows that is 2. Everything else is isolated. Okay, we're talking about reduction. So the first thing you need to take note of is this is an ester. So esters are part of group 2. So they need a strong reagent. And our only strong reagent is LiAlH4. This is kind of an unfair question because we didn't learn about these two, but we did learn that NABH4 cannot catalyze this reaction. So again, this question is kind of unfair because of C and D, but we learned that NABH4 cannot reduce an ester. So that's why that's the answer. All right. This question. So it's saying which of the following would be completely ruled out as a product of an addition reaction, and we know it's an addition reaction because we're talking about 1,3-butadiene, and we're reacting it with HCl. And when we do this reaction, we absolutely cannot add Cl to the double bond. So we could add it anywhere except directly on the double bond. So this guy would be ruled out. And I mean, that's the correct answer, but it's the correct answer because it gets completely ruled out. And this one has to go back to 19 after this one. Okay. So this guy is the starting material. We could go this way or we could go this way. This is the activation energy. This is the potential energy, right? We know the one with the lowest activation energy is the kinetic product. So A equals kinetic. And the lowest potential energy is the thermodynamic product. So this one is also the thermodynamic. So it's asking that which of the following is true in a reversible reaction. So the less stable product forms more rapidly. No. The more stable product forms more rapidly. Okay, that looks good. Product D will be predominant at equilibrium. No, because B sucks. The intermediate has a short lifetime. We don't know that. So the only one that makes sense is B, because the most stable product, thermodynamic, is formed first, kinetic, and it's the same product. I know I went over that kind of fast, but does that sort of kind of make sense?
Yeah, it does. I just have a quick question. So I've noticed that for the most part, all of the like diagrams, they have the kinetic and the thermodynamic product as like the same one. So will there ever be a situation where it won't be like the same?
So for this class, no, it's pretty much always this.
Okay, thank you.
You're welcome. Okay, and then someone asked for 21. So we already went over 21. This is a weird question because we haven't learned about C or D, so I don't think it's completely fair. But what you're supposed to know concept-wise is that NABH4 cannot reduce esters. It can only reduce aldehydes and ketones. So this is an annoying question, but that is very okay. All right, so let's try to get a couple more in. All right, so for this one, we are doing a reduction reaction. We have a ketone plus LiAlH4 and water. So that means we turn this guy into an OH. We're not going to change the stereochemistry here at all. All we're going to do is make OH, H. So we started with a double bond. Double bonds are planar. So can we choose whether the hydrogen gets added wedged or dashed? Yay or nay? So since the double bond is planar, when we add the hydrogen to that carbon, can we decide if it added wedge or dash, or is it going to do both, or is it going to do neither? It can add either way. Yes, both. Cool. So this one stayed the same. This one, they changed it up. This one, it stayed the same. This one, they changed it up. So those are canceled out because we're not touching this guy at all. And then we could either add wedged or we could add dashed. So both of those are correct. So it's a mixture of 1 and 3. Does this make sense-ish? Also, if anyone has questions, let me know. When is this due?
December 1st.
Swaggy. Okay. Wait a second. I'm so sorry. I had a realization just now. When is December 1st? I am a mess. Okay, that's next Wednesday. All right, so we can finish this on Monday. Katrina got me a birthday present and she gave it to me today. And she was like, I hope you enjoy your weekend. Happy birthday. And I was like, oh, that's so funny. Katrina was early by a week. My birthday's next weekend. My birthday's literally this Sunday. Oh my God. I can't believe it's the end of November already. I feel like I'm gonna die. Oh my goodness. Thank you very much. I have, ugh, I literally thought it was like the first week of November. I cannot believe it's the last week. I wish my birthday was near Halloween. I think the reason people thought it was near Halloween was because I said we're all gonna dress up and have a party for my birthday. But no, I literally meant like next Monday, we're all gonna dress up and have a party. Sorry for the mini existential crisis I just had. And thank you to everyone who said happy early birthday. You guys are so sweet. And yes, I am a Sagittarius. And funny story, I had a student one time who asked me when my birthday was, and I told him, and he went, oh, you're a Sagittarius? And I went, yeah. And he went, that makes a lot of sense. And to this day, I don't know what he meant by that. But, you know, it'd be like that, I guess. I don't actually. I can look it up. All right. So does anyone have any specific questions before I let you go? Okay, cool. So you are free to go. I will stop the recording and I think I'm going to post it. Yes. I just want to